May, we had a 74 average, but we didn't really believe that was accurate because we had some people that went into the testing center, stayed there for 6 or 7 minutes, and then left.
Yeah.
And so that wasn't really a good reflection of what we knew.
So
It turns out that 93% of the class took that first exam. And after the second exam, the average for the class went from 74% up to 80%, a very respectable average. And the number of A's went from 182 to 265. Now, in my morning class and this class, combined, we had 503 students. So more than half of the students in the two classes got an A on the midterm. The number of perfect scores went from 16 to 20. And the biggest change, the most important change, was that the number of failing grades was cut more than in half. And so that showed that there was a lot of advancement there. It turns out that only a little over half the class took both exams. And, you know, given that 93% of the class took the first exam, what that means is that a lot of people that did well on A just decided this is good enough. I'm not going to put myself through B. 74% of the people that took both increased their score by an average of about 15%. Okay, and that's doctored, but not in the way you think it's doctored. What I did is I went in and I pulled out any gains that were made by people that took less than 30 minutes on A. You know, if you went in and just looked at A and then left, you know, you're going from a 15 to a 75. That's not real gain. That's just, you only took one exam. So I took those out, and still we had an average advancement of 15%. So good job, all. Good job. Now, the final exam is not really a final. It's another midterm, just on the stuff that we're covering from now till the end of the semester. It's another midterm. And the bad news is that the university policy really won't allow us to have an A exam and a B exam. Our exam has to be open for the whole final period. And so it's just going to be a one-shot. Make believe it's exam A and you're not going to take exam B. Okay. Are there questions on the exam or? Yes, sir.
Yeah, but.
With that?
That's like scheduled.
So, like.
The test is scheduled from the beginning of the finals week, which is the 12th, to the end of the finals week, the whole time, all open. Yeah. Okay. I hope everyone saw my email where I sent a link to the solutions to the exam B, where I went through all of the problems step by step, so that you could see how they were supposed to be done. Would someone be willing to give us an opening prayer to get us started today, and pray that the first row doesn't get blown up when we blow up the can? Thank you.
Our dear Heavenly Father, we're grateful that we could all be here today. We're thankful that we could learn here. Please help us be able to feel the Spirit and learn a lot in this lesson. And we say these things in the name of Jesus Christ. Amen.
Thank you. Okay. We're going to skip over chapter 9. We'll come back to it after Thanksgiving. But we're going to jump to chapter 10 and talk about fluids. Fluids being liquids or gases. And I have a challenge here, and that is that a lot of what we're going to be covering in fluids seems familiar to you. You know, we're going to be solving problems involving sinking and floating. And you probably covered that in the second grade. And so it's going to seem like, oh, this is old news. But my experience over many, many years, and there have been a lot, is that on that next exam, the problem that is missed more than any other one is the sinking and floating problem. Okay, I'll show you before the end of this lecture that there are some problems that are just tricky. Okay, they're tricky. In the morning, I asked a question and we use clickers, and in the morning class, every seat is full. And we had 5 people get it right. So there's some learning to be done is what I'm trying to say in an awkward way.
Next week.
Turn to your neighbor and introduce yourself again, but this time find out their middle name. Find out their middle name.
Yes.
I don't have a middle name.
Okay, now some of you found yourself sitting next to someone who didn't have a middle name. We named our daughter Heidelinda as a first name. We figured it would be cruel to give her a middle name. So if you're sitting next to someone that doesn't have a middle name, just for the rest of this class period, call them Nimrod. No, that's not an insult. It means mighty hunter. And in Montana, that's a group, that's everything. Okay. Nimrod. Okay. Nimrod. So ask Nimrod real quick how they would go about finding the area of some surface. What would they do to find the area?
About my name.
You guys gonna be okay helping with the demo? Okay. Are any of you sitting next to a Nimrod that said length times width? Yeah, there's a Nimrod. Okay. Okay. So I have a deal for you. On the side, I sell farms, and I've got 2 farms for sale. Both farms are identical as far as the dirt and the water, all the farm things that are important that I don't know about because I'm a city boy. Okay. So the only thing you have to worry about is which one is the biggest. Which one are you going to get more for your money? And if we look at that farm number 2, length times width, that seems to work. Okay. But if we look at farm number 1, length times width is going to suggest that, whoa, that's really a good deal. So clearly that formula works for rectangles, not so much for different shapes. And so what we need to do in those cases is break everything up into rectangles or squares in this case. If I were to say, break everything up into 1 acre lots, and then I just count how many acres I've got. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So when you find yourself adding the same number over and over again, that's the time to multiply. Okay, so I've got 8, and I've got 8, and I multiply and I get 64. And that's why length times width works for rectangles. But for farm 1, I've got to go in and say 1, 2, 3, 4, 5, 6, 7 and a half, and 2/3 and 3/4, and okay, I've got to add them up. Now, for today's lecture, we're not so worried about area as we are about volume. Volume is what we need to talk about. And we're going to generalize what we did with the squares and instead talk about cubes. And these cubes are 1 centimeter by 1 centimeter by 1 centimeter, cubic centimeters. Okay. Now, if I wanted to find the volume, the space taken up by this little pumpkin guy, the simplest way intellectually not practically, but intellectually, would be to take a bunch of these cubic centimeters, make a block, pull out a carving knife, and if I could carve really well, I would make an exact duplicate of that guy out of these cubes. And then I would pull the cubes apart and count them. Careful to count, well, this is only a half one, this is 2/3, 3/4. And that, you can imagine, would take me all day, even if I could do it. So it's simple in theory, but not in practice. The volume of an object is just the number of unit cubes, 1 centimeter cube, needed to make a duplicate. Okay? So there's got to be a better way. To find the better way, I've got a demo that I call the 75-25 rule. And that's because when I do this demo, 75% of you are going to say, whoa, I've known that since the 2nd grade. That, oh, trivial, that is. But 25% of you are going to have a mind-blowing experience. You're just, okay. Now look, I don't want you to make eye contact with Nimrod, because if you're having a mind-blowing experience, I don't want Nimrod to know, because you should have had this in the 2nd grade. Okay. Here's the demo. I've got 2 identical objects. Are they indeed identical?
Yes.
Yes. Is he lying to us? Would you hold them? Are they identical?
Sure.
No or heck no? Oh, heck no. This one has 1 pound of lead shot in it. This one has 1 kilogram of lead shot in it. Much heavier, much heavier. Now I'm going to lower these into these 2 beakers that are filled to the same level with colored water. And what I want you to think about, don't talk to Nimrod, don't make eye contact, is in which beaker is the water going to rise the most? Okay, think of your answer. Here we go. They went up exactly the same. Of course they did. Okay. How much water got pushed up is determined by the volume, the size of the object. And indeed, the 2 objects were the same size. They were both the same bottle. They just weren't the same mass. Okay. And it turns out if they are fully submerged, the mass don't matter. Okay. The weight doesn't matter. Okay. It's just the volume, the volume. Now that gives us another way to find the volume. If I submerge something, the object displaces an amount of liquid equal to its volume. Now, what do we mean by displaced? Well, if I were to start with this full to the brim and then put it in and measure how much spilled out, that would be displaced. That's messy. So instead I say, well, I started at 550 milliliters. In the end, it's up here at 900 milliliters, and I take the difference. You've done that in chemistry classes in high school and middle school. Okay. Now, I learned this principle later in life than I should have. I asked my grandmother to teach me how to bake an apple pie. She's just the best baker in the world. And I'm glad that I had that chance before she passed away. But while I was learning, she asked me to get a cup of Crisco. It's lard, okay? And so I got a measuring cup and I started scooping out the Crisco and pushing it into this measuring cup. And those of you that are bakers know that doesn't work very well, because there's air pockets and you're trying to get them all out of there and get it full. And my grandmother laughed at me. She said she was laughing with me, but I wasn't laughing. And she said, Greg, that's not the way you do it. So she got a great big measuring bowl and filled it up to 3 cups. And then she started putting in Crisco and pushing it under the water until the water level went up to 4 cups. And suddenly I had a eureka moment. Well, the first person to have this eureka moment. Oh, and just to prove that I can make a pie, there's a pie that I made. Yeah, the geeks in the room see it, don't you? Yeah, That's a pie in a pie, right? Okay. Now, here's the story of Hero of Syracuse. You've all heard it before, but I'm going to read it to you again. He decided to place a golden crown in a temple to the god. He measured out a certain mass of gold and gave it to an artist to make him the most beautiful crown in the world. The artist returned with this beautiful crown. The mass of the crown was identical to the mass of the gold that Hero had given him. However, Hero suggested that this artist had cheated him, had replaced some of the gold with silver. Why? Because it was a poor artist. Now, he was unsure how to detect the theft, so he asked the local smart guy, Archimedes, for help. As the story goes, Archimedes was lowering himself into a tub to bathe, and he observed that the more of himself that he lowered into the tub, the more water ran out of the tub. When he made that observation, Archimedes supposedly leapt from the tub, ran down the streets naked, yelling, "Eureka, Eureka." This was not such a big deal in Greece. It's bigger deal in Provo. Don't do it. Okay? So, Archimedes goes back to the king and he proposes the following test. He takes a lump of gold and a lump of silver, each which had the same mass as the crown. He first placed the silver lump in a vessel full of water and measured the water which ran out. He then did the same thing with the gold and finally with the crown. And what did he find out? Does anyone know the end of this story? No? The artist cheated the king and he lost his head. So, not a happy story. Not a happy story. Well, let's talk about some basics. The concept of density. Density is nothing more or less than the amount of mass contained in 1 unit of volume. Now, the MKS units of volume are meter cube, but that's huge, okay? And that's just not a real convenient unit to use. So we're going to use units of grams for each centimeter cube. Grams for each centimeter cube. Now, in those units, does anyone know what the density of water is? Anyone remember that from their chemistry class? Yes. What is it, Rebecca?
Per ml.
What's that?
Gram per ml.
1 gram per centimeter cube. 1 point what?
Same thing. I said ml, sorry.
What's that?
I said ml.
Oh,
Cube.
yes. Grams per ml is exactly the same as grams per centimeter cube, except it tells people that you're a pre-med student, okay? So if you're a pre-med student, you should probably say grams per ml, okay? Milliliter. So it's 1 point what? 1 point what? Let's be more specific. 1.0 what?
One question is
1.0000000 to infinity and beyond, okay?
Mhm.
That's how we define the gram, okay? We had already defined the meter and hence the centimeter by the length of some king's, I don't know, foot. Anyway, that's not neither here nor there. But the way we define the gram is the mass of the water that would fit in 1 centimeter by 1 centimeter by 1 centimeter. But it has to be special water. It's not just tap water here. What's special about it? Anyone know the special nature of this water? What is?
Standard condition.
Okay. Nothing. Okay, finally. Brave soul back here. What's that? It would be better if it's distilled water, but that's not the most important part. Anyone else? Howard? Okay. The temperature. The temperature. What temperature does it have to be?
5 degrees Celsius.
4 degrees Celsius.
Darn.
That's kind of arbitrary, don't you think? It turns out that water is very, very special. It's different than other fluids in that water gets more and more dense as it gets colder and colder. Well, all fluids do that, okay? But the thing is, it only gets more dense down to 4 degrees. And then as it goes from 4 degrees down to 0, it actually expands. And that special character of water is what keeps the fishes alive. If you think about it, in the winter, as the water gets colder and colder, when it gets to 4 degrees, that's the most dense, and that sinks to the bottom. Okay, and so because of that, the pond or the lake freezes first at the top, not at the bottom. If water acted like other things, where it got denser and denser all the way down to freezing, we would freeze from the bottom up and kill all the fish. Okay, so good thing about water. Now, so it's 1 gram per cc, cubic centimeter, 1 gram per centimeter cubed, or 1 gram per milliliter. Those are all equivalent. In MKS units, it's 1,000 kilograms for every meter cubed. And that's a lot, 1,000 kilograms, a metric ton. And that's why your landlord doesn't want you to have a water bed on the 2nd floor. Okay, not that water beds are a thing anymore. Okay, our first clicker question. Get your clickers out. Which has the larger density, a cup full of water or a lake full of water? It's not a hard question. Oh, and while you're answering that, I'm going to start boiling this water. Now we've got flameage.
Probably should take it back.
Okay.
Oh, and actually, it's really.
Okay, they have the same is the correct answer. Good. Okay. So fluids are defined as liquids and gases, and the difference between liquids and gases, they both conform to the shape of their container, but for liquids, their volume is conserved, whereas for gases, the volume can change. And so liquids take the shape of the container while maintaining a constant volume, proving that cats are liquid. Well, it's supposed to be funny. Okay. How many of you are scuba divers? Okay. When you scuba dive, one of the problems that you sometimes have, if you've got problems with your sinuses, is that as you go deeper in the water, the pressure gets so large that it feels like your head's going to explode. I always had that trouble when I was scuba diving in Guam as a teenager. And so let's talk about that pressure. What do we mean by pressure in a liquid? Well, if we take the push and just take the part of the push that's perpendicular to your surface, to your body, and then you divide that by the area of your body, that's going to give you the pressure. Okay, it's the force acting perpendicular to the surface divided by the area of that surface. Now, back in the day, long time ago, Disneyland had a ride that was truly, truly pathetic. It's called 20,000 Leagues Under the Sea. It was a swimming pool, and they had a make-believe submarine. You got in that submarine, and everyone had a little porthole. And then they tooled around this little swimming pool, and they would put bubbles up in front of your window so that you were dive, dive, dive. And then they had plastic fish that were tied to the bottom of the swimming pool. It was not Walt Disney's best work. Okay. Now, but it's instructive, in that if we think of that window, if we take the total push of the water in and divide it by the pi r squared of the window, that would give us the pressure of the water. There would be another pressure due to the air inside of that submarine, and I would just take the total push of the air divided by pi r squared and get the pressure out. If I take the difference between those, it would give me the net pressure on the window. Okay? Now, what should matter as I dive? Well, it turns out that a lot of things that we think should matter don't. Okay? All that matters, it turns out, is how deep you go in the liquid and the density of that liquid. And how deep you go, I can demonstrate with this little device here. I've got water in here and 3 different openings. And if I open this opening, it just kind of trickles out. If I open this one, I get it coming out with much greater pressure. And then this one down here, even more. Okay. Now, I'm going to stop that. Otherwise, we're all going to be running to the bathroom. Okay. That one stopped itself, huh? Okay. Get that out of the way. I'm going to need that later. Okay. My good friend Jeff Adams, his family, they're Canadian, and they bought a summer cabin on a lake. And he decided, being a geek, as a teenager, that he was going to explore the bottom of that lake. And so he came up with a plan that was just ingenious. He was really confused why Jacques Cousteau had not thought of this. He went and he got himself a garden hose and stuck it in his mouth. The other end of the garden hose he put through a piece of styrofoam so it would float. And then he weighted down his shoes and walked out into the lake. Does anyone see a problem with this approach? Gonna work? If you think about the hose and the pressure at the 2 ends of the hose, down there where the Jeff is, it's a very high pressure. Up there at the top of the lake, it's a low pressure. And so the air in the hose is going to go from high pressure to low pressure. This is a great way of getting all the air out of the Jeff. And that's the way it works. Okay. So that did not pan out. Okay. So let's find this relationship between depth and pressure. What we're going to do is we're going to go to a pond, and with our minds, with our imagination, we're going to carve out a chunk of water. And that chunk of water is going to have area top and bottom of A, and the pressure at the top is going to be P1, and the pressure at the bottom is going to be P2. And our gut's telling us from our scuba diving experience that P2 is going to be bigger than P1. But how are they related? Okay. Now, if I do a free body diagram, I have 3 forces. Well, I've got horizontal forces, but they all cancel out. Okay. For vertical forces, I've got 3. I've got the weight down, mg, and I have the pressure on the top down times its area. If you think about that, pressure is how much total force there is for each 1 unit of area. And if I multiply that by how many units of area I've got, that'll give me the total push down. The 1 force up is the pressure due to the water below this chunk times the pressure times its area. Now, the thing about this chunk of water, it doesn't know it's special. It doesn't know it's different from its neighbors. And so it's not going up, it's not going down, it's just sitting there. And so if I balance these 2 forces down with this one force up, I get this equation here. Now, the mass of that chunk, I can write as the density of water times the volume of that chunk. And the volume of that chunk, I can write as the area, top and bottom, times the height. And when I plug that in, lo and behold, every term has the area in it. And so I can divide both sides by area, and I get one of the most important equations for your toolbox for the final exam. That's one you need to have, okay? Now, what that means is that it doesn't matter whether I dive down in a pond or whether I dive down in the Great Lakes. If I go down 5 meters, it's the same in both. The area of the body of water does not matter at all, at all. Now, the way we use this equation is that if we know the pressure at one point, we can find the pressure at another point by plugging into this formula. And typically, we take P1 to be at the top of the lake or pond. Now, the pressure up there is not zero, because when you're at the top of the lake, you're at the bottom of a vast ocean of air. And air is a fluid, and that's going to cause pressure. And that pressure that it causes is atmospheric pressure, okay? And it turns out that that atmospheric pressure is not negligible. It's 101,325 newtons for every meter squared. But remember, a newton is a fifth of a pound, and a meter squared is big. And so a newton per meter squared is a small unit. We call that unit a Pascal to honor a dead professor. Not a bad thing to do, okay? Not a bad thing to do. Now, because that unit is so small, we typically talk about kilopascals. 101 kilopascals would be the atmospheric pressure in standard units. But here in America, we call that 14.7 pounds per square inch. Okay. Good sir. Remind me of your name. Nolan? Logan. I wasn't even close. Stand up, please. This bar has a weight of 14.7 pounds, and it has a cross section of 1 square inch. So if you just hold out your hand, okay, and just, okay, that's a lot of pressure, is it not? Imagine that much pressure on every square inch of your body, and that's the reality we live in, okay? Now, not really, stay up there, Logan. Okay. That's what it would be at sea level in Los Angeles, okay, where they're really under a lot of atmosphere. We're up a mile high in Provo, and here it's only 12.4 pounds per square inch. And so let's see what that feels like. More better, right? Yeah. What I'm trying to say is it's better to live in Provo than Los Angeles, okay? Don't go home. Stay here. Okay.
Like Los Angeles.
Now, that atmospheric pressure also explains why when you step in mud, suddenly you're stuck. Okay. Did it ever make you wonder, well, how can a little bit of mud keep me from getting where I want to go? Well, if I'm walking on a regular surface, there's nooks and crannies under my shoe that allow the air pressure to get in there and push up on the bottom of my feet, about the same as the air pressure pushing down on me due to this 14.7 pounds per square inch. And so I'm able to just walk freely. But when your foot gets stuck in the mud, we remove that air pressure from the bottom of your foot. You still got the air pressure pushing down on you, and so you're stuck. I've got this rubber mat. If I put it down on this, I can lift things, because there's, no air in between there. I've got pressure pushing up on this side, pressure pushing down on that side, pushing them together. If I let any air in, it drops. Okay? Now, let's crush this can, shall we? Brinley, you want to help me with this? This is a 55-gallon drum. It's steel. And what we're going to do is, Brinley, if you could get some gloves on there. And actually, while I'm putting the cap on, if you could put some more ice in that tray so that we've got enough ice. Now, because that had been boiling, it pushed all the air out of the can and replaced it with steam, water vapor. And we're going to cool that steam down so that it condenses back into a little tiny bit of water in the bottom of the can, leaving a vacuum behind. Let me get my gloves on, and we're going to lift that up onto the ice. Whoop, whoop, whoop. Slow man. Okay, you're ready, set. Okay, perfect. Now, they should have given me more ice. Well, it is what it is. Okay. Well. We're doubters, weren't you? We're doubters. Yeah. Okay. Are you believers in atmospheric pressure? Yeah. And it's still crushing. Still, oh, what? Okay. Now, I just want to point out that in Dr. Benyon's class, they crushed that. Okay. I only had one drum this morning, and I crushed it in the morning class, and I thought, you know, I'm feeling bad for the afternoon class because I don't have a drum. So I went on Facebook Marketplace. I found a drum. I bought it. I went and cleaned it out in time to get back there 15 minutes before class. So this just, yeah. Oh. Life is good. Can you imagine teaching math? Oh, okay. That's in case it didn't work. Okay.
Wait, let's see it.
Now, that's not the biggest example of this atmospheric pressure. In Germany, they did this. Okay, now that was not an accident. Okay, those people were standing out in the rain in Germany, They were waiting for it to happen. They had sprayed this thing out with steam, and then they capped it off really quick before it could cool down, and they wanted it to implode. Why would you do that to a perfectly good tanker car? To make a movie. To make a movie. Okay? The first person to demonstrate this atmospheric pressure was Otto von Guericke with the Magdeburg spheres. What he did is he took two hemispheres that were only connected with some grease, and then he used a bellow to pull the air out from inside, leaving only outside pressure pushing on the spheres. And then he hooked up those spheres to two teams of horses who could not pull them apart. Now we've got a much smaller set of spheres, hemispheres. I'm going to suck the air out of them. And then I've got our two horses here. Come on down. Now, guys, you may be strong enough. There's a small but real chance that you can pull these apart. So plan your life accordingly, you know, kind of find a nice soft place to land, or just leave a leg back so that you don't land. Okay, grab a side and 1, 2, 3, go. Oh, yes, they are. Let's give them a hand, folks. Okay, and they broke it. Oh, there it is. Oh, man, that's going to come out of my salary. Okay. Good. Thank you, guys. Okay. Now, this is very similar to one of your homework problems. How deep do you have to go in water before the pressure increases from 1 atmosphere to 2 atmospheres? In your homework, you're in a lake of alcohol. It's in Las Vegas, okay? But here we're just going to use water, okay? And so to solve that, we use that grand high equation that's in your toolbox. We want the pressure down here to be 2 atmospheres. So that's P2. If I subtract 1 atmosphere from both sides, I get this equation. And if I solve that for H by dividing by the density and the gravitational field strength, I get that equation. Now, because G is 9.8 newtons for each kilogram, I'm going to have to use MKS units for the pressure. And so I'm going to use 101,325 newtons for each meter squared. And I'm going to have to use the density of water in MKS units, 1,000 kilograms per meter cubed. And if I do that, I get 10.3 meters or 34 feet. How many of you learned that in diving school? Okay. Now, that's not the number you really want, because that means you're diving in freshwater lakes, and that's boring. That's just mud and rocks, okay? If you are going to be in salt water, it's a flat 10 meters. Now, what if instead of water or salt water, you happened upon a lake filled with liquid mercury? How deep would you have to go in liquid mercury to increase the pressure from 1 atmosphere to 2 atmosphere? The very famous number they taught you in nursing school, okay? 76 centimeters or 760 millimeters of liquid mercury, okay? Less than a meter, because liquid mercury has a density that's more than 13 times that of water. And this, because of that, this is the way we used to make barometers to tell you about when the weather was going to change. We would take a long tube, a glass tube, and fill it with liquid mercury, and then put a container on top and turn it upside down. Now, the the column of mercury would fall until the pressure here is equal to the pressure there. Now the pressure outside is due to atmospheric pressure. The pressure inside is due to this column of liquid mercury, assuming that there's zero pressure up here, that this is a vacuum. Now it turns out this is not a total vacuum. There's mercury vapor up there, which turns out to be toxic, and it causes brain damage. Now, why am I bringing that up? Because when my brothers and I were young, my father, the dentist, would bring home liquid mercury for us to play with. And while we were waiting for supper, we would push this liquid mercury around the dining room table. And that explains my family. There's some damage there. We just didn't know. We didn't know. Now, that's 760 millimeters of mercury on a sunny, beautiful spring day at sea level. Okay, at sea level. I've told you before, I went to high school on Guam, and below our house was one of the most beautiful beaches on the island, Panguithan Beach, and it just gorgeous. And next to the beach, you see this little power station here. It had a canal that was cut through the reef, and that turned out to be important because this reef was brutal. I mean, it was just rock like that, okay? And if you were trying to come in over the reef or go out over the reef and the waves hit you, you were just torn apart. And so what we would do is we would jump in this canal, and it went all the way past the reef where all the interesting wildlife was, the octopi and things like that. Now, why am I telling you this? Because often when I'm in my office with a smile on my face, just staring into space, that's where I'm at. Okay, that's my happy place. Let's imagine that I'm back there and I lift up, for some reason, a great big boulder. And I want to take that boulder down to the ocean. So I'm walking across. Oh, the sand is hot. Oh. But now my feet are in the water. Oh, that's better. And then as I go deeper and deeper in the water, something magical happens. I'm becoming stronger. The salt water is making me stronger so that the boulder doesn't feel it's heavy. What's going on here, folks? The buoyant force, which is the topic of this week's tutorial, okay? The buoyant force. Now, let's talk about that buoyant force. That blue represents the water, okay? And this is what boulders look like in Guam. They're very regular, okay? And so what you see is that as you go deeper, the pressure and hence the push by the water in the neighboring area of the boulder gets larger. But I think we can argue that these forces cancel out these forces on the left, and the forces on the front cancel the forces on the back. What doesn't cancel is the force pushing down from the water above the boulder and the force pushing up from below the boulder. I'm always going to have more force pushing up. And so in tutorial, what we do is we replace all of those pushing forces by the water into one force that we call the buoyant force. And then we ask ourselves, how big is that buoyant force? How big is it? Now, Archimedes was the first person to figure this out. And we're going to do it the same way he did, but with different language. I'm going to ask us to consider a boulder of 1 meter by 1 meter by 1 meter. And then instead of a boulder, I want you to think of that as a Casper box. Do any of you remember Casper the Friendly Ghost? Was that too long ago? Okay. I'm old. Every now and again, Casper the Friendly Ghost would be trying to break up a fight between the cat and the fish, and somehow he'd swallow the water and the water would be inside him and the fish would be inside him, but he'd save the fish, okay? A Casper box just holds stuff, but it has no mass of its own. So if I fill this Casper box with water, how many kilograms of water can I put in 1 meter by 1 meter by 1 meter? Well, that's the density of water. I can put 1,000 kilograms of water in that space. How much does 1,000 kilograms weigh on Earth, whether it's water or anything? Multiplied by G. And so that's going to be 10,000 Newton. Now, here's Archimedes' genius. He said, that box full of water doesn't know it's special, doesn't know it's different from the rest of the water. So it's not going to go up, it's not going to go down. And that means that the buoyant force has to be 10,000 newtons. And then he said, well, what if instead of water, I put steel in there? Well, steel has a density that's 7.8 times that of water. And so that's going to weigh a whole lot more than 10,000 newtons. Indeed, it's going to weigh 78,000 newtons. But here's what Archimedes said. What's in the box doesn't matter. The buoyant force is from the outside water pushing on the box. It has nothing to do with what's in the box. And so when I ask how big is that buoyant force, it's still 10,000 newtons. And now this free body diagram is screaming down. And that box full of steel is going to race to the bottom of the lake. If instead I fill that box with styrofoam, styrofoam has a much smaller density than water. And so let's say that the weight is only, I'm making that number up, 1,000 newtons. Well, again, the buoyant force doesn't care what's in the box. It's the push by the water outside the box. And so I'm still going to have 10,000 newtons of buoyant force. And in that case, I'm going to accelerate up towards the top of the lake. Okay. Now, I love this far side here. Embedded in styrofoam shoes, Carl is sent to sleep with the humans. It's just said. Now, Archimedes' principle is just what you think it is. The buoyant force acting on an object is equal to the weight of the fluid displaced by the object. Or in other words, the weight of the liquid that would fill the Casper box that's the same size and shape of your object. Okay? Now, the consequence of that we saw is that an object with greater density than that of water will sink in water. And an object with a smaller density than that of water will float in water. And that's what you should have learned in the second grade. See if Nimrod learned that in the second grade. Do a buddy check. Yes, Logan.
Good.
This number comes from
The weight, yeah, because it's a force. But I get it through the density. If I knew the density of styrofoam, I could use that to get the mass of styrofoam. Then I'd multiply that by 9.8 or 10. For density, density is the mass divided by the volume. And so if I multiply both sides by volume, mass is just density times the volume. Yeah. Density is how much mass I have in 1 unit of volume. Then I multiply by how many units I have. Okay. Let's just make sure that we understand what this says. If you are careful, you can set up a cylinder where you can layer different liquids on top of each other. And if you don't bump it too much, you can keep them separated. At University of Washington, where I was 35 years ago, we had a big cylinder, about 5 feet tall, that we had 5 different layers in. Now, suppose I had salt water, which has density of 1.2 grams for each centimeter cube, And on top of that, I had fresh water with a density of 1 gram per centimeter cube. And on top of the fresh water, I had oil with 0.9 gram per centimeter cube. And then I had 3 objects. The density of those objects is given here. And I carefully, so I don't bump this too much, I carefully lower these things into my cylinder. Where will they end up? Talk to your neighbor, talk to Nimrod. Where do they end up? Okay. So object A has a density less than that of the oil, so it floats on oil. Object B has a density greater than oil but less than fresh water, so it sinks in the oil but floats in the fresh water. Object C has a density that's greater than fresh water but less than salt water, so it ends up at that boundary. D and E both end up at the bottom because they have a density greater than salt water. My point is, it's always going to be either at the bottom of the liquid or at the top of the liquid. The only way you can get it in the middle of the liquid is if it has exactly the same density as the liquid. And that's hard to engineer. When you're scuba diving, that's why you have that vest where you can let air in or put air out to make you neutrally buoyant, to try to give the same density that the salt water has. Does that make sense? Okay. So, big question, if that ship is made of steel and steel has a density that's 7.8 times that of water, is this a sinker or a floater? Is this a sinker or a floater? Lloyd's of London would like to know. Well, we know it floats, but that seems to violate this physics principle that we just talked about. So we're going to have to redefine what we mean by floating. Okay, if a giant takes that boat and drags it down to the bottom and turns it over and over and over till all the bubbles come out, okay, and then let's go. If it stays down, it's a sinker. If it comes back up, it's a floater. Can we agree on that operational definition? Okay, that'll take some of the ambiguity out. On the internet a while back, these pictures came through. A boat's coming down the river and someone forgets to put up the drawbridge, and as a result, we've got a problem. But this particular boat is a floater, okay? That's a pretty good one. So, quick question with your clicker. The buoyant force is greatest on a 10-ton ship if it's floating in freshwater, saltwater, liquid mercury, or all the same. You can click now.
A little bit.
Thanks, C.
Okay. Get your vote in, last call. Okay, D, all the same is the correct answer. Is the correct answer. Why is that the correct answer? Well, if we look at a free body diagram, the weight force is going to be 10 tons. That's why we call it a 10-ton ship. The only other force acting on it, if it's free floating, is the buoyant force up. And because that ship is not going up or down, it has acceleration of 0. And that means that that diagram has to scream balance. And that means the buoyant force has to also be 10 tons. whether that's in fresh water, salt water, or liquid mercury. But what has to be different in liquid mercury than when you're floating in water? Well, in both cases, I have to displace 10 tons of liquid, but it takes a lot of water to equal 10 tons. And so your boat's going to be low in the water. It's going to be riding low, and it's going to be stable. A lot of the boat's going to be under the surface. Whereas if you were in liquid mercury, heaven forbid, it doesn't take very much liquid mercury to get up to 10 tons. And so not very much of your boat's going to be under the surface. You're going to be riding very, very high, so high that maybe you're not stable and you'll tip over, which would be a real disaster. Okay. Where are these people? What body of water are they in? Any guesses? What's that? Raise your hand so I can. The Dead Sea. It is the Dead Sea. It could also be the Great Salt Lake, because both of those have a very high salt content and hence a high density. And so they are riding high in the water. Quick question. I have three identical, well, they're not identical. They're the same volume and same size, same shape blocks. One made out of steel, one made out of aluminum, and one made out of wood. On which block is the buoyant force the greatest? Talk to Nimrod. On which block? Okay. How many say the steel? How many say the aluminum? How many say the wood? How many say the steel and the aluminum? Good. Okay. The buoyant force is always, whether it sinks or whether it floats, always going to be equal to the weight of the fluid displaced. The steel block and the aluminum block are displacing their entire volume of liquid. Where they are now, water used to be, had to go elsewhere, okay? Whereas the wood at the top is only displacing about half of its volume. So if the buoyant force on the steel was, I'm making this number up, if that buoyant force on the steel were 10 newtons, it would also be 10 newtons on the aluminum, and it would be 5 newtons on the wood, okay? Now, you know the answer, so, okay. It's going to be block A because it displaces more water, okay? And that's Archimedes' principle. But because they're floating, the buoyant force also, by Newton's second law, with zero acceleration, has to be equal to the weight of the object. If these two blocks of wood have the same volume, but they have different weights, that means they have different density, which means one of them might be oak, the one that sinks, floats lower, and the other one might be balsa wood, okay? A high density wood and a low density wood. Are there questions on that? Thank you for catching that. What should I remember if I want to do my, yes, Logan.
This one has a higher buoyant force. Why did this question? Why were they all the same?
Oh, because here, in this problem, it was the same ship in the freshwater, the saltwater, and the liquid mercury, whereas here, these are different blocks. Apples and oranges, okay? What should I remember? Two big ideas. The first one is that Archimedes' principle always applies. Whether it sinks or whether it floats, the buoyant force is always equal to the weight of the fluid displaced or pushed out of the way. The second tool for your toolbox only applies when the object floats. If an object is free floating, the buoyant force is also equal to the object's weight by Newton's second law with zero acceleration. Okay? but that's only true if it's floating, Now, you've probably heard that when you see an iceberg, you only see 10% of the iceberg. What that means is you don't see 90% of the iceberg. And what that tells you, I'll show you on Thursday, is that the density of the ice is 90% the density of the water. Okay? If you can't see, if 90% of it is submerged, that tells you the density of that object is 90% the density of the liquid. Now, again, I'll show you that on Thursday. But for now, I'd like to show you that some of these problems are challenging. Yes, sir.
Before we continue, just some clarification.
Wait.
Before we continue, just some clarification. Is that good?
Okay.
With the ship problem and it floating in the fluids, if we were asked in which fluid does the ship float quickest in or soonest, would that be the fluid that's most dense, or mercury?
What do you mean floats quickest? Are you?
You dropped it in a bottomless pit of the fluid.
Oh,
How quickly does it?
let me ask it a different way. If I were to put that ship down at the bottom, in which of those liquids would it have the greatest acceleration towards the top? It would be in the liquid mercury.
Because it's most dense.
Right. Correct. Okay. And because if it's fully submerged, all of the liquids are displacing the same volume of liquid, but it's the weight that gives you the buoyant force. And the weight of that much liquid mercury would be much greater than the same volume of water. Okay, this is a challenging problem. You're floating in a boat in your very own swimming pool. You're rich. There are 6 gold bricks sitting on the floor of the boat. Again, you're rich. You reach over with a marker and you mark the water level on the side of the pool. And then you throw the bricks of gold to the bottom of the pool. What happens to the water level of the pool? Does it go up, down, or stay the same? With your clicker, one last time. Okay, last call. Make your vote. Okay, stays the same as the winner, but that is not the right answer. Okay, we'll talk about it on Thursday. Go somewhere else.